In this video, we're going to be looking at the distance problem. To help us understand the distance problem, let's look at an example. If I look at a graph of a velocity curve versus time, so here we have velocity and here we have time. So let's say that we are traveling at 60 miles per hour and we're traveling at 60 miles per hour for, let's say, 4 hours. We know if we're traveling at a constant velocity, the graph would look like this. There would be our velocity versus time graph. Now, what does the area under the curve from 0 to 4 represent? Well, if we have a velocity versus time graph and we're looking for the area under the curve, we would just be finding the area of a rectangle, where this here would represent time, that would be 4, and the height of our rectangle would represent our velocity, 60. So we would have 60 times 40, which is 240. And we know if we take rate times time, we get distance. So this would represent 240 miles, the distance that we've traveled using our velocity curve. Now, applying this to what we saw in the last video, what if we were looking for the area under the curve, but we wanted to use rectangles to help us find the area under the curve? So if we were to use rectangles, you can see that we would be able to find the exact values of these rectangles to represent the area under the curve. The width of each rectangle would be 1, and the height of each rectangle would be 60. So this would be 60 plus, this one would also be 60 plus 60 plus 60. So that would give us our total area under the curve, which would be 240 miles traveled. What if we had the same scenario, but this time we don't have a constant velocity? Say our velocity is changing. So if we wanted to find the distance traveled on this interval from A to B, if we're able to find the area under the curve of the velocity function, that would give us the total distance traveled on that interval from A to B. Now we're going to apply the technique that we learned last time. We are going to create these rectangles to help us estimate the area under these curves, which will give us the distance traveled. So we're going to be looking at an example where, well, what if our velocity is not a constant velocity? So here's an example. Suppose the odometer of a car is broken. We want to estimate the distance traveled over 30-second time intervals. We take the speedometer reading every 5 seconds and record the following. So when we start at time 0, we see the velocity of 17. 5 seconds later, we record our velocity, 21 miles per hour. 10 seconds, we record the velocity, 24 miles per hour, and so on. We do this for a time interval of 30 seconds. Now, our time interval is our velocity is in miles per hour and our time interval is in seconds. So let's get a common unit for these, for our velocity and our time. So let's say we're going to change this into, we'll put time, which is in seconds, and we'll put velocity, which is in miles per hour. We'll change the velocity to feet per second. So if we made the conversion, we would get, and our conversion you can see is down at the bottom here, we would get the following table. So we're converting 17 miles per hour into feet per second by multiplying 17 times 5,280 divided by 3,600. That's how we'll convert to feet per second. So when we make the conversion, now we're in feet per second. Now, let's think about how we would find the area under the curve graphically, and then we'll do it. We'll look at finding it numerically. So if we drew a velocity versus time graph, we know the velocity is in feet per second, time is in seconds. So I'm going to say this is 5, 10, 15, 20, 25, and 30 seconds. And then let's plot those points. So I'm going to make a unit of, let's say this is 10, 20, 30, 40, and 50. So if we plot those points now, we would have 0, 25, 5, 31, 10, 35, 15, 43, 20, 47, 25, 46, and 30, 41. Now if I just connected these points with a smooth curve, it may look something like this. Now there are two ways we could go about finding the area under the curve. We could use the right side of the rectangle and draw our rectangles in and use the area of these rectangles to approximate the total distance traveled on that interval. This would be using the right side of the rectangles. So to find the area of this first rectangle, the width is 5, and then we're going to be looking at, well, if we plugged this value into our function, if we plugged 5 into our function, we would get 31. So we'd have 5 times 31. That would be the area of the first rectangle. Plus, the width of the second rectangle is 5. And if we plugged in 10 to our function, we would get 35. Then the next rectangle, the width is 5, and if we plugged in 15, we would get 43, and so on. So we'd have 5 plus times 47 plus 5 times 46, and then we would have the last one, which would be 5 times 41. So this would give us our estimate for the area under the curve, which represents the total distance traveled. And this would be using the right side of the rectangle. Now we could do this same process, but we could use the left side of the rectangle. Let me see if I can erase this to use the left side of the rectangle. So if we erased these rectangles because now we're going to use the left side of the rectangle instead. Missed. All right, so let's see if we can get these out of there. Okay, now we're going to draw the rectangles in so that the left side of the rectangle is touching the function. And I think I'm going to use a different color, so the left side of the rectangle now will be touching the function. So we would have this rectangle, and the left side of the rectangle, this one would be touching, and so on. So now we can see that the left side of the rectangle is touching the function. And if we were to do these calculations, still the width is 5 times, but now notice we're going to be using this value. This is the height of the rectangle now, so we'd be using 25 instead, plus the width. Now the height of the next one would be when t equals 5, so now we'd be using 31. And if we proceeded this way, we would have 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 46, and that would be the area of the last rectangle. And this appears it would be an underestimate. When we use the right side of the rectangle, it appears that we would have a little bit of an overestimate. So now let's look at that process that we just went through numerically. So we can calculate those values. And when we calculate those values, there is using the left side of the rectangle, and then there's the right side. So you can see if we use the left side of the rectangle, we get 1,135 feet, and if we use the right side of the rectangles, we get 1,215 feet, our over and our under estimate. But that's the total distance traveled over the interval 0 to 30 seconds. So to calculate total distance traveled, if we had a variable velocity, it's changing on us, then we can see the rectangle is looking at the left side of the rectangles because we're starting at 0. So f of t sub 0 times delta t. This is the calculation that we just performed to find the total distance traveled. And you can see at the very end of the rectangle it's written also in summation notation. And notice the f of t sub I minus 1, we know that would be using the left side of the rectangles. Now if we wanted to get a more accurate answer, we could decrease the number or decrease the width of the rectangles to get more rectangles, and we could get a more accurate answer. So it seems reasonable now that if we took the limit of the summation of those rectangles and we took n rectangles and then let n go to infinity, that would give us the total distance traveled on that interval.